Hello friends, and welcome to the channel Derive. In this video we're going to derive the formula for the centripetal acceleration. Why is it that AC equals v squared over r? First we will derive the magnitude of the acceleration vector, and then we will derive its direction. So consider we have a circular motion just like this, and an object being here, and after a while, call it delta t, ending up over here. So what we have is first a positional vector here. We can call it r0, an initial positioning vector, and then after a while we have a final position vector here. We can call it rf, and this angle will of course change. We can call it delta theta. At the same time, we will have a velocity vector here, of course. We can call it v0 for initial, and after a while we will have a velocity vector here that we can call vf. Important thing here to consider is that the speed, that is the magnitude of the velocity vector, is constant. So anywhere along this path the speed will be constant. But the velocity is not constant, of course, because the direction of the velocity vector changes all along the subject's course along this circular motion. So because the velocity vector changes, that means that we must have some kind of acceleration going on here, because remember that acceleration equals a change in velocity over a change in time. What else does this formula tell us? Well, it tells us also that the direction of the acceleration vector, because the delta t is just a scalar vector, the direction of the acceleration vector will be the same as the direction of the velocity vector here. And that's an important thing that we'll need later on. Okay, so let's draw some triangles here. First of all, what's important to consider is that the velocity vector is always perpendicular to the position vector. So we can draw the triangle of the position vectors. First we have r0, we have rf, and then we have the resultant vector here. We can name it as delta r, and this is the displacement, of course. And then we have the delta theta, that's the angle that changes. Then we have the other triangle, which is the initial velocity vector here, the final velocity vector here, and the delta v, the change in velocity vector. And this angle will actually, because these two vectors are perpendicular to each other, this angle will also be delta theta. That's quite obvious, but I can draw it for you so that you see that's a fact. We can consider a triangle with one side being the initial velocity vector, the other side being the final vector. These are not to scale, of course. And then we can draw the velocity vectors here as well. Here, velocity vector, we can extend it like this, so we're interested in this angle. We can call it x, because we know that this angle is delta theta, so we need to prove that delta theta is x, of course. And this is 90 degrees because we've said, remember, that they're always perpendicular to each other. And this must also be 90 degrees, of course, and you know that the sum of the angles in a circle is 180, which means that that equals delta theta plus 90 degrees. And what's this angle? Well, this is of course 90 minus x, so plus 90 degrees minus x, and these cancel out, which leaves us with x equals delta theta. Another important factor to know is that the magnitude, what's the magnitude of the position vectors? Well, that's of course the radius. The radius is the magnitude for each one of these position vectors here. So that's r and that's r as well. And what's the magnitude of these velocity vectors here? Well, we said that the speed is constant all around the path, the circular path of this object, which means that the magnitude of these velocity vectors, that's just v, the constant speed. So we have two sides that are equal in this triangle, and we have delta theta, which means that we have an isosceles triangle here, and we have the same angle here, delta theta, and two equal sides, which means that these two triangles are similar triangles, which gives us the possibility to have some nice ratios between these two triangles. For instance, we can write that delta r over r is actually the same as delta v over v. This is an important expression. And we would like to have delta v on one side, and that will of course be delta v equals, we move up r, v over r times delta r. And then we have this formula right here. This formula right here, of course. Important thing here to know is that we're talking about magnitudes all the time. Magnitudes of these vectors. Magnitudes. So what we're going to do is that we will replace this with this expression, and we will get, we can write it down here, create some space, that the magnitude of the acceleration vector is, so instead of this we will write this, v over r times delta r, the magnitude of the change in the position vector, divided by delta t. And now we will focus on this expression. That's an interesting expression, because what does it tell us? It tells us a change in position over a change in time. So it tells us, and it changes, and it tells us about the magnitude of change, which means that this, since this is a scalar vector, is talking about speed. It's talking about speed. So how can we relate this to what we've said before about the constant speed for this object? Well, if we let delta t move towards 0, what does that mean? Well, that means that delta r will be infinitely small as well. It will be just a dot along the course of this object. And what we're calculating is actually the velocity, or the magnitude of the velocity, the speed for each point along the trajectory of this circular path. And we will achieve that by letting delta t move towards 0. This essentially means that this expression, when delta t moves towards 0, then delta r over delta t will become v, which is the constant speed. And if we insert v instead of this expression, we will get that the magnitude of the acceleration vector, equals v squared over r. So now we have proven why the magnitude of the acceleration vector is v squared over r. Next mission is to prove that the direction is always pointing towards the center of this circular path, because that's what we've been taught, that it will always point towards the center, the AC here. And why is that? Well, if we create some more space here, and if we turn to this triangle again, then we can write that the initial velocity vector here, final velocity vector here, and the resultant, the change in the velocity vector here, with this delta theta. And we've said before that the magnitude of these two vectors is the same, which means that it's an isosceles triangle, with these two angles being the same, we can call these two angles alpha. This gives us that 2 alpha plus delta theta equals 180 degrees. And what we want to know is the direction of the change in the velocity vector, because if we know that, then we will automatically get the direction of the acceleration vector, because remember, delta t is just a scalar, it doesn't have a direction. So we must calculate the direction of the change in the velocity vector here, delta v. And we want to do that again by letting delta t tend towards 0, because we want to calculate the acceleration, the instantaneous acceleration at any point along the circular path. But what happens when delta t goes towards 0? Well, when delta t goes towards 0, then this object will only have been traveled a very short distance, and in other words, an infinitely small angle here, which means that when delta t tends towards 0, then delta theta will tend towards 0 as well. So what we'll end up with is, for the instantaneous case, for the instantaneous point along this circular path, is that 2 alpha equals 180, which means that alpha equals 90 degrees. What does this tell us? Well, we've said before that the angle alpha is the angle between the change in the velocity vector and the initial velocity vector here. And that angle will always be 90 degrees, which means that if we have an initial velocity vector here, then the angle for the change in the velocity vector when delta t tends to 0 is and will always be 90 degrees. And because the direction of this vector also is the same as the direction as the acceleration vector, this means that the acceleration vector will always have a 90-degree angle in relation to the initial velocity vector. In other words, it will always, no matter where we are along the circular path, be directed towards the center of the circle. Always directed towards the center of the circle. So now we've proven both the magnitude, we've derived the magnitude of the acceleration, centripetal acceleration vector, as well as its direction. I hope you found this video helpful, and don't forget to like and subscribe, and see you in the next video.